Hey everyone, I am Sanskar Thakre from class A2, batch V2, and my roll number is 36, and I welcome you all to my video. Today we are diving into some of the most powerful concepts in linear algebra: eigenvalues, eigenvectors, Hermitian matrix, and unitary matrix. This topic might sound heavy, but don't worry. By end of this video, you'll understand why they are so important and how they are used in everything from quantum mechanics to machine learning, 3D graphics, and even data compression. We'll start with the basic intuition behind eigenvalues and eigenvectors, then explore what makes Hermitian matrix special, and finally see how unitary matrix help preserve the length and energy in transformations. So if you want to strengthen your maths foundation and truly understand how basic science behind the modern technology works, make sure you watch till ends. So let's get started. So our first topic is eigenvalues and eigenvectors. So the first question is, what are eigenvalues and eigenvectors? The eigenvectors can be referred as the vectors whose direction stays the same after the matrix transformation. And eigenvalues can be referred as how much the eigenvector is extended or shrunk. It is a scalar value. So basically हम इसे एक रबर बैंड के एग्जांपल से समझ सकते हैं. तो ये रबर बैंड किसी भी डायरेक्शन में एक्सटेंड हो सकता है, बट अगर हम इसे किसी एक पर्टिकुलर डायरेक्शन में एक्सटेंड करें लाइक दिस, सो ये जो डायरेक्शन है विच कैन बी रेफर्ड एज आइगन वेक्टर्स, एंड ये लेंथ जितना ये एक्सटेंड हुआ है इससे हम आइगन वैल्यूज के हिसाब से रेफर कर सकते हैं. सो दिस इज अ बेसिक एग्जांपल जिससे हम समझ सकते हैं आइगन वैल्यूज एंड आइगन वेक्टर्स. नाउ द इक्वेशन ऑफ आइगन वेक्टर्स एंड आइगन वैल्यूज. So basic equation is A times V is equal to lambda times V, where A is matrix, V is eigenvector, and lambda is eigenvalue. This means applying matrix A to vector V just multiplies it by a number lambda, no direction change. So let's see how to calculate eigenvector and eigenvalue. So this is a step-by-step method for solving 2 into 2 by 2 matrix. So take A as A, B, C, D, and then subtract lambda times I from A. So then it will become like this. Step 2 is finding determinant. See, so if after we finding determinant like this, I hope you all know how to find determinants. And step 3 is set determinant to 0. To take all this value and equal it to the 0. After solving this quadratic equation, we will find two roots. That two roots can be referred as eigenvalues. So this is very simple method to find eigenvalues. Hope you'll understand. So after all this, we get some of the interpretations, and which can be referred as below. In shear or rotation, the most vector change direction, but eigenvector don't change any direction. Second is, if lambda is equal to 1, direction will not change. And if lambda is equal to 0, direction will collapse to origin. Diagonalization makes power like a raised to the power 100 easy. Just some of the interpretations which we get from previous slides. Then next, where are eigenvalues and eigenvectors are used? This is the most important question. So eigenvalues are used in Google PageRank, face recognition, stability of system, quantum mechanics, vibration analysis, PCA, machine learning dimensionally and dimensionality reductions. So this is all the place where these eigenvectors and eigenvalues can be used. Now let's move to the next major topic, Hermitian matrix. Hermitian matrix is a complex version of symmetric matrix. A matrix A is Hermitian if it equals to its own conjugate transpose, which can be referred as a given equation. This means a diagonal element are always real. Off diagonal elements are complex conjugates. Hermitian matrices are extremely important in quantum mechanics because they represent the measurable quantities like energy and momentum. Let's discuss the key properties of Hermitian matrix. Eigenvalues are real if the matrix contains the complex entries. Eigenvectors corresponding to the different eigenvalues are orthogonal. They behave like symmetrical matrices but are defined for a complex number. The model physical observables which must have real outcomes. This makes Hermitian matrix central to physics, engineering, and advanced mathematics. Okay, next let's move to unitary matrix, another fundamental concept in linear algebra and quantum Next, let's move to unitary matrix, another fundamental concept in linear algebra and quantum computing. A unitary matrix is one whose inverse equal to its conjugate transpose, which can be given as this such equation. This means a unitary matrix preserves length, magnitude, angles. You can think of unitary matrix as the rotations in a complex space. Just like orthogonal matrix preserve the shape in a real space, unitary matrix preserve shape in the complex vector spaces. Unitary matrices are extremely important because they represent the transformation that do not lose information. That's why quantum state involve using the unitary matrix. In quantum computing, every gate, Hadamard, Pauli, Silot is unitary. The key properties include their eigenvalues lie on the unit circle, means having magnitude 1, their column from an orthogonal set. They preserve probability and energy in physical systems. Another important point is that unitary matrix makes computation stable. Since length and angle don't change, the numerical error don't amplify. This is why Fourier transformation, signal processing filter, and quantum mechanics rely heavily on unitary matrix. Let's summarize everything we learned today. Eigenvalues and eigenvector help us to understand the natural behavior of matrix. Hermitian matrices have real eigenvalues and represent the physical observables. Unitary matrix preserves length, probability, and structure during the transformation. Together, these concepts form the mathematical foundation of quantum mechanics, quantum computing, machine learning, and many branches of engineering. Thank you so much for watching. This is Sanskar Thakare, and I hope this video helped you clearly understand the concept of eigenvalues, eigenvectors, Hermitian matrix, and unitary matrix. Thank you for watching my video.